So on to our speakers programme, and our two speakers this afternoon that are really going to have a hard act to follow. But first I'd like to invite our RES 2015 Group G award winner, Professor Louise Harra from UCL, without chaperone, who is going to talk about exploring solar activity with the Hinode Spacecraft. Over to you, Louise. Make sure we get connected.
You're chaperoning me.
Well, I can stand here while you talk if you like.
It's not connecting actually. So
They'll sort you out in a second, won't they?
Welcome to 2016. This is very hard to follow, I have to say. So I'm here to give you a summary of the results from the Hinode space mission. Hinode was launched in 2006, so we have celebrated recently 9 years of very healthy science from it. The UK contribution is the EUV imaging spectrometer, and that's what we're here to celebrate today. For those of you who were at NAM last year and attended the conference dinner, John Culshaw was there giving the entertaining speech at the dinner. I cannot possibly replicate the way he speaks. Unfortunately, I'm not that entertaining. But one of the things he did say when he was describing the summary of Hinode Ice was, it sounds wonderfully impressive. And I think that's a nice summary because it is a wonderfully impressive instrument and it has worked incredibly well to date. So the purpose of the Hinode spacecraft is to study the sun. And we've already heard a little bit about the history of people studying the sun. It looks in the optical, so you can see three instruments sketched in this cartoon. The big optical telescope was the first time an optical telescope was ever put into orbit to study the sun. Our instrument is at the top in blue, and that purpose is to study the dynamics of the corona, so measuring spectroscopically. The importance of spectroscopy was already mentioned, which was nice. And then we have the X-ray telescope at the bottom there. So it's three instruments, but I'll concentrate mostly on the EUV imaging spectrometer, so you'll get to see some spectra. And just to show you the fun bit of building the instruments, so this was obviously a while ago. The top image here, this is showing the actual spectrometer. And for those of you that visit MSSL, you'll see an engineering model of the instrument in the corner of the common room. So it's a long instrument, it's 3 meters long, and it had to be that long in order to get the resolution that we required. You can see the guys in the bunny suits here, and also it attached to the spacecraft here. So that's to give you an idea of how long it had to be, how big it had to be. So it's taller than me, heavier than me, in order to be able to achieve what we've achieved with it. So the instrument works in a number of different modes, and this is one of the modes that I'll show you. So it has, it's a spectrometer in extreme ultraviolet, and it has slits and slots. So it has a very high resolution slit that will give you really nice spectra with high spatial resolution, and then you can blur the spectral direction, and that will give you a wider spatial view. So this is showing you the slot data, and it's showing you in different temperatures, so the different colors give you different temperatures. So we've got a cooler temperature is blue, and then slightly warmer temperature green, and then hotter temperature is red. So you can see that mix, and you can see its solar minimum when we launched. We launched, and then solar activity pretty much died, except for one big flare when we were commissioning and didn't really want to have to be active. So solar activity was pretty low, and mentioning Maunder actually, talking about people were making bets as to whether we were going into another Maunder minimum, because it lasted quite a while. And then the image on this side shows you the solar maximum. So you can see the min max, and you can see how you can see different features when you look at different spectral lines in the sun. And this is a lot of what we've been doing, is to look at in different spectral lines, different temperatures, and to understand the dynamics during the solar cycle. So ICE has worked flawlessly for 9 years. We're only reaching the point now where we have to do our first spec out, so this is a real credit to the engineers involved in the build. We have over 900 refereed publications have been produced. There's 12 institutes across the UK use ICE, and 14 nations across the world use ICE. I quite like the instrument. So when we got the first full spectrum, what really surprised us is we kind of thought we knew this wavelength range reasonably well. So this is EUV. We've observed it in the EUV before. We've had stellar spectra in the EUV. Surely we know this region. But when we got the first data down and people were going through the line identifications, we realized about 40% of the spectral lines were actually new. So you get better spectral resolution, you see more things, new things, and you've got a lot to learn from it. So what I'll go through now is several topics which are big questions in solar physics, and describe briefly what Hinode ICE has done to answer some of those. So the first question is, where does the energy come from to heat the atmosphere and drive the solar wind? We already know that comes from the magnetic field, but we don't know exactly where and how. So one of the things with ICE that was discovered, we have this lovely imaging data from the X-ray telescope here. And this bright region here is an active region, so it's a region above a sunspot. And at the edge, this dark region here, if you can see spurting material at the edge. When you look with a spectrometer, you're not quite sure what this is, but when you look in the spectrometer, here we have intensity and here we have Doppler velocity, with blue being upflow, red being downflow. So when you look at these regions, which are quite dark in the images, you always see this upflow. So we know that you've got material that is moving upwards. Why we're interested in that is because we want to know where the solar wind comes from. If we've got material going up, does it actually get out into the solar wind? So there's a lot of people working on this. There's a lot of publications and have happened on this. So these outflows, so these blue shifted regions, occur at the edges of active regions, and they occur where magnetic connectivities change. So it goes from a closed loop to an open field line. It will occur in the regions between that. And in terms of understanding their characteristics, because it's a spectrometer, you can work out its temperature. So here you've got a mixture of hot and cold material. This is the cold and this is the hot. So if you look at those movies and you look at the edge here, so this is where the stuff is spreading outwards, you can see it more clearly in the hotter stuff than the cooler stuff. So the flows are hot. So we've got hot stuff and hot stuff leaving the sun. And it's very dynamic. You can see when you look at this. This is with the slot data again. If you look at the actual spectra itself, so this is one spectral line here, and this is at X marks the spot here, and it's in one of these regions where you've got this upflow. And as you can see, it's very dynamic. If you watch this, you'll also see in the blue wing that you'll get this kink asymmetry occurring, which occurs on and off. It's not consistently there, but it comes and goes. It's very dynamic. The velocities change. You can see the velocities here, the white dots here, so you can see how it varies. And this is the line width as well, which varies with time. The line width is a good indication of dynamics and also potentially turbulence. So it's something that we measure a lot, and I'll be showing you quite a bit of. So this is work that appeared in The Economist. The Economist pounced in this work for a reason. So this is when we were able to look at the abundance. So we took a full sun raster, so full sun spectrum, which took a while to build up as a small field of view instrument, and then you're able to measure essentially the abundance. So you want to measure the abundance at those regions where you've got the upflows occurring, and then is that abundance consistent with the abundance that's measured in a slow wind itself? So the abundance that we can measure close to Earth, are we actually seeing the actual source? It's very hard to link it up because we're imaging the sun, and then you're measuring those in situ measurements close to Earth. So things have traveled 1 AU. But this is what was done, so you can look at these regions here, which are red in the abundances. That's slow wind measurements and values. And you can see this very strong blue as a strong upflow. And the results are consistent. Those regions where you've got the strong upflow are the regions where the abundances are consistent with that measured in a slow solar wind. So we're getting to the point with slow solar wind that we know some of the regions where it actually comes from, which is a difficult thing to measure. So the next mystery of the sun, how are solar flares triggered? This is a tough one. And it's one we really want to know. The amount of energies that are produced in solar flares is the biggest energy source in the solar system. And there have been various ideas put forward about magnetic reconnection. Maybe is that going to work? Yeah, whoops. So this animation here is showing you the concept of magnetic reconnection occurring high in the corona as one idea put forward. And people have been trying to test that in different ways because there are issues to do with the magnetic reconnection model that are not consistent with the observations, so we want to be able to understand it further. There are various things that are consistent. For example, if you look, this is flashing through different spectral lines. So this is an imaging spectrometer, and each of those pixels, you've got one of those spectra that I showed you in the previous slide. So you're able to measure all these different parameters at each pixel. But this shows you at each of these different temperatures that you're seeing different structures. And one of the things we want to be able to measure at the reconnection point where you've got the field lines connecting, do we see any evidence of that? Do we see any turbulence? Do we see anything that indicates that that's occurring there? And we do. There's been measurements of both turbulence at the loop tops and also inflow, which you would expect when you've got the field lines reconnecting. The other thing that we've looked at is the actual trigger phase. So when you see movies of a flare and a coronal mass ejection, this is full sun data from SDO-AIA, and this is our flare source here. And I'll play that again. You see these global structures occurring. So it starts small scale and it gets big. So we wanted to try and see what the really early phase was spectroscopically, what actually happens before the event is triggered. So in this case, we're looking at this field of view. So we're looking in at the flaring region itself. And what you see when you look at that, so if you look at it pre-flare and then as the flare goes on, you can see when the flare is occurring because this starts to get darker, it's stronger, the values are higher. So this is a measurement of the turbulence essentially. And this is when it goes completely bananas, to use a technical term. But at the beginning, you'll see this region here starts to become strong. And that's a region that's away from the actual flare site. So we wanted to know what that was. And when we looked at it, we could see that it was related to the region that actually erupted later on. So we could see that build up in the activity in a flux rope, which we can measure through dimming regions afterwards. So you've got an eruption, material leaves, and things become darker in certain areas of the solar disk. And those regions, we could see those turbulent patches at the edges, and we could track those. So we could see that right at the beginning of this particular eruption, you could measure the activity occurring very early on before the actual eruption occurred. So we could do the same thing with coronal mass ejection sources. So you've got intensity measurements here, Doppler velocity here. This is where the flare occurred. So this bright region here, bright and velocity here, is where the flare occurred. Over here is where a lot of mass erupted and left the solar disk. So we were able to measure quantitatively exactly what bit left, if you like. We could measure the speeds, what could actually leave the sun, and then work out what the magnetic field was in those regions, and then make the comparison with the in situ data, where we're measuring the magnetic cloud as it goes past the Earth. And what disturbed me more than anything was they were very consistent. So the numbers were equal. So this measurement is reasonably accurate in that one example. So the next mystery of the sun, how does the solar cycle work? So we can see this beautiful images of the sun from when we launched, going through in time to solar maximum, which wasn't a very exciting solar maximum, we have to say. It wasn't as active as we've seen before. And that is interesting in itself and something that we wanted to understand. So one of the things we could do with the optical telescope on Hinode, which is quite neat, because this is a vector-magnetograph, you can essentially measure at the poles as best as you can possibly do. because as everybody in this room is curious, you want to be able to see where you can't see already. We can't really see at the poles, so you want to try any way you can possibly manage to see what's happening at the poles, because that drives the solar cycle, drives the activity. So in this case, we've got North Pole 2008, 2011, South Pole, roughly the same times. And the different colours are showing you different polarities at the poles. So what was happening is you've got one pole. If you look here, the polarity was starting to change. If you look here, it was staying the same. The South Pole was lagging behind in the polarity reversal. So there's this sluggishness in the South Pole. It was being lazy compared to the North. We wanted to see if we could measure that and how that changes during this period here. So we know that the magnetic polarity reversals in the Sun occurs, but it recurs in this kind of sluggish. It tries to reverse, and then it reverses. So there is a bit of a period where you can see this mix here. We wanted to see what's happening during those periods where you've got these streams, the end of the sunspot groups leading the lagging edge, heading towards the poles, how that was changing. So we wanted to see, did that change the dynamics? So we looked at the poles with ice, so we wanted to measure the coronal dynamics. One of the neat things about spectrometers is that you can see things that you can't see in intensity. So it's like looking into a secret world in a way. So here's intensity. If you look at this, you can see a bright spot here, bright spot here, bright spot here. If you look in the spectral data, you see this really interesting region here which has the strongest dynamics. There's diddly squat in the intensity, there's nothing there. So you wouldn't necessarily know that was an interesting region by looking here. But in the spectral data, it's strongly dynamic, but we can't see it any other way than through the spectral data. So we wanted to see those streams going to the poles, whether we could see any difference in this kind of behavior, these kind of stealth jets, if you like. So the magnetic nulls, if you look at the global magnetic field, you can play with the modeling to look at magnetic nulls, which are regions where you're most likely to get magnetic reconnection occurring, and that will change as the cycle changes. So this is a difficult plot to follow maybe, but this is latitude here. So this is the polar region, and this is the year up here. And as you approach solar maximum, you expect to see more of these nulls at the poles because things are becoming more chaotic in the global magnetic field. And that's what you see in the magnetic nulls. When we look at the coronal dynamics over the same time period, we see fluctuations in those dynamics, but there's nothing increasing with solar cycle. It basically stays consistent during that whole period, during minimum, during maximum. There's always dynamics there. It doesn't necessarily change with cycle. So that has an impact in our understanding of what happens, what drives the cycle. So we have these very small scale things that are always there, and then we have the more global things on top of that. So it does have an impact in understanding the dynamo, and DISMECs want to explore the poles more in the future. So ice is currently observed for nearly a full solar cycle, and there's no reason why I can't carry on because the instruments are healthy, the spacecraft is healthy. We get the occasional threat of being hit by some debris above us, which is alarming, but we've only had to maneuver once. But aside from that, it's going okay, so that's good. And to the future, we've certainly learned from Hinode that having spectroscopy through the atmosphere is something we really need. What we have with Hinode is we're measuring an optical telescope at the photosphere, so you measure magnetic field. Then we have this gap, and then you measure higher up in the atmosphere, and you're measuring the spectra there. We don't know what's happening between those layers. So the next generation telescope is Solar C, and I didn't mention it at the start. Hinode was called Solar B before it was launched, and then was christened after one successful orbit. So Solar C is the next big thing, and there's been a lot of work put into designing the telescopes so that you can get spectroscopy right the way through the solar atmosphere. So all those features that you see where you've got dynamics, you've got the solar wind created, you've got all this hot stuff, you've got solar flares, you want to understand where the magnetic field is coming from, what drives it, and how that energy is transferred out into the corona and into interplanetary space. And Solar Sea will certainly help do this. The next mission, I've talked about the poles a bit. Next mission that will do that, which we're getting close to, and I was at a review just before I came here on Solar Orbiter. It's getting to that phase. We're in the high-level build phase of Solar Orbiter. We deliver our instruments to the spacecraft at the end of this year. It will be launched, hopefully, October 2018. It will be orbiting the Sun, gets in as far as 0.28 AU, and especially, as well as getting up close, it gets out of the ecliptic. So those polar regions that are currently reasonably mysterious to us, we'll be able to finally peer down with remote sensing instruments and measure with in situ. So there's a lot to look forward to. And at that I'll stop. And that image will make you sick after a while. But that's to show you what view we will get, because we go into 0.28 AU and then out to 1.1 AU. So we have a very elliptical orbit, but hopefully you can get a feel that we will be seeing out of the ecliptic, and we'll have this interesting way of running instruments that we don't currently have. So thank you very much for listening.
So Louise has kept very nicely to time, so there's time for a few questions. Lindsay, right at the back there.
This observation that you made of the non-thermal broadening in the larger area around the flare, what do you think's going on there? Have you got an interpretation for this? It's quite surprising to me. But
the non-thermal velocity, it had its ends were in the ends of the dimming region. So our interpretation was that that was where the flux strip was that we couldn't see before it was activated. So that we were seeing something in the turbulence that we couldn't see in the intensity.
But why should the flux stroke be turbulent before an eruption? That's really my question.
Dynamic. It has to get its energy from somewhere, so there's a build-up before it goes. So it's showing dynamic as opposed to turbulence as such.
Anybody else? Obviously answered everybody's questions today. Okay, so let's thank Louise again.
Thank you.
And